You know, taking a massive AI model and customizing it for your own specific task has always been a huge bottleneck. It's expensive, it's slow, and it's just super resource intensive. But what if you could just cut that training time in half? Well, today we're going to dig into a new system called LoRAFusion that promises to do exactly that. So, to really get why this is such a game changer, we got to rewind a little bit and look at the original problem. Traditionally, customizing a large language model meant full model fine-tuning. And that's exactly what it sounds like. You have to retrain every single parameter. This whole process just demands a staggering amount of computational power and memory, putting it way out of reach for most people. And when you look at the numbers, you really see the scale of the problem. Fine-tuning a big model like Llama 3.170B would require over a terabyte of GPU memory. I mean, that's just prohibitively expensive for almost anyone. And this is where LoRA, or low-ranked adaptation, first came in to save the day. It just slashed that memory requirement by nearly 8x, bringing it down to a much more manageable 142 gigs. Now, the way LoRA pulls this off is really clever. Instead of retraining the whole model, it just freezes the original pre-trained weights. Then, it injects these small trainable adapter layers. These new layers add less than 1% of new parameters, which is the secret sauce behind those massive memory savings. It's what really opened the door to custom AI for so many more people. So it sounds like a perfect solution, doesn't it? We get the custom model we want, but without the insane hardware costs. The story should end right here, shouldn't it? Yeah, not quite. Turns out there was a hidden cost, and this 40%? That represents the approximate drop in training speed when you use LoRA. So the solution for the memory problem, it had created a brand new problem for performance. And this was the big mystery. Everyone was celebrating the memory savings, but under the hood, LoRA had actually created this pretty significant performance bottleneck. The very tool that made customization accessible was also, ironically, making it painfully slow. The big question was, why? So as researchers started digging in, they found out the slowdown wasn't just one single thing. It was actually caused by two separate, hidden bottlenecks that everybody had kind of overlooked. And here are the two culprits: redundant memory access and a GPU load imbalance. These are the twin problems that LoRAFusion was built from the ground up to solve.
Okay, let's break down that first one. Think of it like a chef in a kitchen. Full model fine-tuning is like a smart chef who grabs all their ingredients at once. But LoRA was acting like a chef who walks back and forth to the pantry for every single spice. Even though the new LoRA layers are tiny, they've forced the GPU to constantly read and write these huge chunks of data, called activation tensors, from memory over and over again. And all this inefficient back and forth actually increased total memory traffic by up to 2.6 times. Just wild.
Now, the second bottleneck pops up when you're using multiple GPUs. Imagine you're packing moving boxes with a friend. If you give your friend all the light, easy stuff and you take all the heavy, awkward books, your friend's gonna finish super fast and then just stand around waiting for you, right? Well, that's exactly what was happening with LoRA. Some GPUs would get these short, easy training examples, finish their work, and then just sit idle, waiting on the other GPUs that got stuck with the long, hard ones. So with both of these problems clearly identified, the stage was set for a new hero. And this is where LoRAFusion enters the story, a system designed specifically to go after these two hidden inefficiencies. LoRAFusion's strategy is actually pretty elegant. It's a two-level fix. To deal with the memory problem, it uses smarter, custom-built computational steps they call fused kernels. And to fix that workload problem, it uses a smarter scheduling system to coordinate multiple training jobs at once. Let's start with that first fix. How do you stop the GPU from making all those wasteful trips to and from memory? The answer is something called kernel fusion. So essentially, instead of telling the GPU to do step A, then write to memory, then read from memory to do step B, kernel fusion just combines A and B into one single seamless operation. This totally eliminates those wasteful memory transfers. And LoRAFusion uses this clever split graph method to apply this fusion only where it's needed most, on the memory-intensive parts, while leaving the main heavy-duty compute operations alone so they can still run at peak performance. All right, now for that second problem, those lazy GPUs just waiting around. To fix this, LoRAFusion introduces a component called the multi-LoRA scheduler. You can think of this like a hyper-intelligent warehouse manager. The scheduler looks at multiple different LoRA training jobs all at once. It then strategically packs the data from all of them together into these things called microbatches, making absolutely sure that each GPU gets a perfectly balanced mix of long and short sequences. It even has a final step to merge any leftover bits and pieces to make sure zero GPU power goes to waste.
So these solutions all sound great in theory, but, do they actually work in the real world? Let's take a look at the results.
Well, the numbers really do speak for themselves. Compared to Megatron LM, which is a really standard framework for training these huge models, LoRAFusion delivered an end-to-end speedup of up to 1.96x. That's nearly double the performance.
And the comparison gets even more impressive when you put LoRAFusion head-to-head with MLoRA, which was the previous state-of-the-art system designed specifically for handling multiple LoRA jobs. Even against this specialized competitor, LoRAFusion was up to 1.46 times faster. So it doesn't just outperform the general tools, it outperforms the specialists too.
Okay, these speed-up numbers are awesome, but what does this actually mean? What's the tangible impact for the people who are out there building and using this tech?
Well, what this means in practice is huge. AI experiments that might have taken a week could now be done in just a few days. The cost of renting those powerful GPUs, it could be nearly cut in half. And maybe most importantly, when developers can try out ideas faster, the whole pace of innovation just accelerates. The authors of the paper really summed up their goal perfectly with this quote. The whole point of this work isn't just about making things faster for the sake of speed. It's about making this powerful AI technology more accessible and more efficient for everybody, from academic researchers to the engineers out there in the field.
And that leaves us with one final, really provocative question. This technology effectively doubles the speed and halves the cost of personalizing the most powerful AI models that we have. So what kind of completely new applications, new services, and new scientific discoveries is this going to unlock? What would you build?